So in this video, I'm just going to be covering some of the material from chapter 32. We're going to start off with AC, which is alternating current. Here, we're used to seeing our battery source looking like this, where the current is just flowing in through one direction and then in that same direction like this. Here, we have this symbol with this little squiggly line in it, and it's saying that the current through that circuit is flowing through one direction, and then it's switching directions after a certain amount of time. How fast it is switching directions is related to omega here, which is the angular frequency. It's related to the frequency by omega is equal to 2 times pi times f. So this is the full expression where this is the voltage at any given moment in time. It's equal to delta V max sine omega t. If we were to look at an AC circuit with a resistor like this, we'd want to figure out what is the current going through that resistor at any given moment in time. We're going to use Kirchhoff's loop rule to figure that out, where we have delta V here, so this gain in potential, minus the drop in potential here is equal to 0. These two values here, I'm using lowercase letters because we're talking about instantaneous moments in time. If we're talking about the maximum values like this, we're going to use the capital letter. Anyways, this is our expression, and we want to figure out what is I. To do that, of course, we just isolate for it, and we know that delta V is equal to delta V max sine omega t. Plug that in, and then we get the current at a certain moment in time t equal to I max sine omega t. And of course, the potential across this here is equal to the potential across the resistor as well, written out like this. What we see when we compare them is that the current and the voltage are in sync. They reach their maximum values at the same time. This is also called being in phase. If we look at a plot like this, it becomes a little bit more obvious, where here in purple this is our current and in blue this is our potential. So when it's at its max, the current is also at its max. Another way of looking at this type of plot is through a phase diagram, where these are phasors, and a phasor is just a vector whose length is proportional to its maximum value. So here this is delta V max, so this is delta V max. This is I max, this is I max. And then they are aligned because they're in phase. And then here they're rotating with a certain frequency, which is omega. Okay, so this is kind of just like a snapshot of what's happening, just to see are they in phase or are they not in phase, and then of course they're rotating as well. Now something to keep in mind here when it comes to AC circuits is that talking about the average current is not really useful. If we look at this graph here, we see that the current is positive when it's going out in one direction, and then it's negative when it's going in the other direction. If we were to average all of this out, we would just get a value of 0. So instead, what we talk about is the RMS, or root mean squared current, where what we do is take all the values of the current, we square them, we take the average of that, and then we take the square root of that whole thing. So I RMS is equal to I max over square root of 2. All I did was simplify this a little bit, and I get this value here. I can do the same thing when it comes to the potential, so I can talk about the root mean squared value of my potential. It's equal to delta V max over square root of 2. So then whenever I'm calculating something like the average power, I'm not using the average current, I'm using the RMS current, like shown in here. Now we're going to move on to talking about a little circuit that has an AC source here and an inductor. We're going to do the exact same thing though, where here we have this potential gain, delta V, and then we have this potential drop of delta V sub L, where delta V sub L, we learned last week, is equal to negative L di over dt. So here again, delta V minus L di over dt is equal to 0. We know that delta V is equal to delta V max sine omega t. All we're going to do now is figure out what the current is across that inductor, so what is I. To do that, we need to take the integral from both sides, and we get that the current is equal to delta V max over L integral sine omega t with respect to time. So then here we take this integral and we get negative cosine omega t. We want to be able to compare the current to the potential, so we're going to change this from cosine into sine. So negative cosine omega t is equal to sine omega t minus pi over 2. So then when we compare these two, we see that they are no longer in phase. They're out of phase by pi over 2 rad, or 90 degrees. If we were to just plot them, we'd see that the current lags behind the voltage by 1/4 of a cycle. So then if we look at the voltage reaching its maximum value here, the current is not at its maximum. The maximum value for the current is way down here. Like it's trying to catch up, but it's not going to. It's 1/4 cycle behind. So here, for instance, if we look at, let's say, the maximum value of I, well, we're actually at delta V is equal to 0. Okay, so there is this lag happening that can be represented by these phasors too, where here, this is delta V max, and this is I max, and here they're separated by 90 degrees, and they're rotating in this direction here. Now, if we look at this expression for I max is just going to occur when sine of this is equal to 1. So here we have I max is equal to delta V max over omega L. This is a very similar expression to what we've seen when it comes to Ohm's law, where we have I is equal to delta V over R. So what we see, or what we say, is that omega L is very similar to the resistance. So we're going to say that it has the units of ohms, and it acts like a resistor in a sense. We're going to give it its own expression or its own letter. So X sub L is called the inductive reactance, and it's equal to omega L. So then, of course, we just rewrite that, and we plug that in here, and we see that I max is equal to delta V max over XL. Now, what does this actually mean physically? Well, remember that an inductor is just a solenoid here. So whenever we have this large omega, what we're really saying is that we have current that is changing rapidly from one direction to another. So here, the current's going in this direction, and then it's going to switch, and then it's going to go through this direction. As omega increases, it means that this switching is happening more and more rapidly. And remember that this inductor, it's reacting to that change in current. And the larger that change of current, well, the more it's going to react. And it reacts by producing a backwards EMF that's slowing down that current. So then the faster the switching is happening, the larger that R value, or that the resistance. It's not really resistance, it's a little bit different, but it's similar in the sense that it's kind of going against that flow of current. So larger omega, larger XL. Let's now look at a very similar thing when it comes to a capacitor in an AC circuit. Same process, we want to look at Kirchhoff's loop rule. We have delta V here minus delta VC across here, which is equal to Q times C, and that's equal to 0. We isolate for Q, and we get Q is equal to C delta V max sine omega t. We want to talk about the current, not the charge, and we know that they're related through I is equal to dQ over dt. So again, all we have to do is take the derivative of this, and we get this here, omega c delta V max cos omega t. Same thing, we don't want a cosine, we want a sine. So we see that IC, the current across the capacitor, is equal to omega c delta V max sine omega t plus pi over 2. So again, there's this out of phase by 90 degrees, but here it's the current that is leading the voltage. If we want to look at I max, it happens when this value here is equal to 1. So I max is equal to omega c delta V max. We're going to put it in the same form as we had last time, where we have delta V max on the top and then 1 divided by omega c on the bottom. So this is kind of like the resistance again. We're going to call it the capacitive reactance, and it's actually the opposite of what we had with the inductor. So here, when we have lower frequencies, we actually have a higher capacitive reactance, so it's acting like it has this higher resistance. We can write the same thing again, where we have I max is equal to delta V over XC. Now the way to remember which one is leading which, what I mean by that is here, current is leading voltage, and then here it's voltage that is leading current, is by using this sentence, Eli the Iceman. So what I've highlighted in yellow, those are the components we're talking about. So here we're talking about the inductor, here we're talking about the capacitor. This is the EMF is in front of the current, so the EMF is leading the current by 90 degrees. And then here it's the current that is leading the EMF by 90 degrees. In the next video, we're going to put all of this together and talk about the RLC series circuit.